So it turned out my phone did need an update to the iOS 17. So it wasn't reading it. All right, so let's see. So describe how you find the volume of the following solids. So think about what it is that you would have to do to find the volume of these solids here. I gave them to you. There's this bad boy. There's this guy here. I'm trying to make it as straight as possible. And then let's say there's this one right here. There we go. These are perfectly parallel, okay? They're straight and horizontal. So if you had to find the volume of those shapes, what do they all have in common? How would you find the volume? Remember the volume, not the surface area.
Find the equation of line. Yeah. And then multiply that. But that's very hard. And also not unless you're given. You'd have to take because of how you'd have to take like half of it. Like you would do with like you would do with y squared, where you take half of it up here, and then you have to like split it, and then yeah. Okay. So when you're taking the integral, right, you have to do it in math. And so that's what I mean with that one. You would have to figure it out, or you're shooting to figure it out. What? I'm like, what is space? What happened?
All right, guys, let's see. These two rows, someone from these two rows. What's your strategy? How would you find the volume of those? Base times height, okay. I guess like if you were to pick this shape, what's the base? This guy right here, right? Okay. So when you say base times height, I like it. So you're saying in this case, this is the base, right? The triangle? Yeah. What's the height? This length or this length? This guy right here, right? Okay, so you're calling this the height. And when you say base, do you mean the length? No, the area. Okay, so you're saying the area of the base, right? The area of the base, okay? So like this bad boy, whatever that area is times that height. Okay? Anyone have a different answer? Different way that they did it. To find the area, yeah, of these shapes. Sorry, the volume of these shapes. Or are you guys all agreeing with Sam? You take the area of the base, and then multiply it by the height. Or in this case, this length, right? Which we're going to call height. Okay, sweet. Yep, that works. Okay, that's what we're going to do. Okay, but I need you guys to keep in mind let's go back to elementary school, okay? And let's say this unit here was a unit of 1, okay? What would be the volume of this slice right there?
The same as the area of the triangle.
The same as the area of the triangle, right? Because the area of the triangle times the height of 1 is just the area of the triangle. So that's something that's going to come up a lot in this section, okay? The volume of something of height 1 is just equal to the area of its base, okay? Now, the reason we get this volume is because you can think of like I'm stacking all these little 1-unit stacks. There's all these slices that I'm using that compose the overall shape of this solid. Okay? So it's kind of like if I had a sheets of paper. Each sheet of paper has an area, right? But when you stack all these sheets of paper, now they create space, 3-dimensional space for a volume. Okay? So that's kind of, I just wanted to plant that in your head because later on it's going to get like all complicated with notation, but I want you to remember this idea. Okay? There are hella visuals in this section, in this chapter. So I created a little packet for all the sections we're going to cover so that you can reference the visuals during while we're presenting all this stuff. Okay? So bring it to class. Don't forget it. I couldn't hole punch it, you know, the 3-hole punch for people that put finder. So I apologize. You guys can do that. Grab one, pass it down. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. For the tablet folks, maybe take a picture of it and add it to your tablet. Yep. Yeah, take a look at all those gnarly visuals. Yeah, that's why I had to take you back to that. Because we're going to use that now like boom. Any extras?
I don't suppose we get this on the next test.
We don't what? Say it again?
We don't get to keep this on the next test.
Well, this is going to be used to understand the stuff that's happening. If you feel you want to use some of it and draw a mini version of it, it's up to you. Okay, so here we go. Oh, I'm gonna need the projector a lot today. All right, give me a second. Let me open this up. Okay. All right, guys. So I'm gonna be using a lot of visuals. Let's see. I have to figure out how to do this. I guess I'll just bring this down. Okay. So let's go back to your Calc 1 days and do a quick reminder of how you found the area under a curve. Okay. So you had your function, and you're more than welcome to annotate the packet as well. Okay. So you have your function. This is the graph of f. You wanted to find the area under this curve. So what did you do? The function itself might have a bigger domain. So what you did though is you restricted its domain to just the interval a and b. You said, okay, I'm going to restrict the domain only from a and b. And then that restricted domain, I'm going to break it up into equal size segments. And normally we use the letter n to say there was n equal segments. Okay. Then what did you do for each little segment? You created a rectangle, and then you guys learned in Calc 1, I can use the left endpoint or I can use the right endpoint. But then you made whatever method you used, you made a rectangle, and then you estimated the area under the curve to be the sum of the area of each of these rectangles. Right? Each rectangle had width delta x, and height was you were given by the y value that you got from plugging in an x value into the function. Okay? So this was basically height times the base. That gives you the area, and so then you added all those rectangles to the sum. And then you said, I'm going to call the definite integral the limit as n goes to infinity, so that these intervals slowly just got chopped up more, so that you started getting an infinite number of rectangles. What happened to the width though, as n was going to infinity? You're getting more of them, so the delta x started getting smaller and smaller and smaller, right? Because the delta x gets smaller and smaller and smaller, it turns out, I don't care if I'm picking the left endpoint or the right endpoint or the midpoint. I just gotta pick a point in the interval to give me my height of my rectangle. So that's why you put a little star with it. You just say some value in between. Okay? Okay, so I'm gonna leave this up here. So I take up a lot of my board today, but it's okay. All right, so let's see. So we got section 15.1, double integrals over rectangles. Keep it short. Rectangles. And so, just so you have it in your notes here, so in Calc 1, you have the graph of some function from A to B. Oh, and then you had all these little rectangles that you moved here. However you want to draw it. Or you don't even have to because I gave you a packet. But then we define the definite integral of your function to be that limit of that funky sum. Okay. So we're gonna start defining a double integral using this similar idea. Okay. So I'm gonna have to jump from side to side so that we can keep this projector. I'm gonna have to work that out. Let me see. Oof. Oh, I don't like that it's taking up most of my board. No, whatever. I just think that we can still see it if you just. Yeah, let me see. Is that okay? Does that look weird?
We have it on our sheet too, right?
Oh, you're right. It just looks a little funky. Okay. All right, guys. So let's see. So how are we going to do this in R3 for functions of two variables? Whoops. I did, huh? Yeah. It's okay. So the video is going to show me though, but it'll still show this. Okay, it's going to be a little bit of a balance. Hold on, I got to think of how I'm going to do this. Because when I taught this last time, my whiteboard was higher. So it kind of helped me. Let me see. Okay, it's okay. I'll screen share when I'm referring to the visual. Okay. All right. So what we're going to do is for a function z equals f of xy to integrate f over a rectangular region R. So if you go to your next visual here, that's kind of what we have. Actually, let me go right here. There we go. So this is the scenario that we're going to be dealing with. The domain of your function might be bigger, right? But you're going to restrict it to only a rectangular region. Okay? And so what you might maybe want to draw next to this picture, or if you want to label it, is you have on the X and Y plane, you have some rectangle R. X will vary from A to B, and Y will vary from C to D. The way that your textbook is going to denote that set R is going to use closed intervals. And let me explain to you how that works. You're just going to say there's a closed interval from A to B cross another closed interval from C to D. This cross is not cross product, and it's not times like in numbers. It means something different that you haven't seen yet. It has to do with something called set notation, called the direct product of two sets. Okay? So. Yep. Yeah, so what you need to realize is, what am I multiplying in this case? Okay? So what this means, though, is it really means a set of a pair of coordinates, a pair here, a point of two coordinates, where the first coordinate is restricted from this first interval. So X is restricted from A and B. That's how you want to read this. So the first coordinate is within A and B, and then the second coordinate is restricted with the other closed interval. Like that. That's how you're going to want to read that, okay? And so basically, just think of this as saying the X values, and this is saying the Y values. All right, so what's the goal? What are we trying to find? Well, this is our goal, guys. We're going to want to find the volume between the surface of your function that's directly above the region R. So we're going to want to find the volume of that solid that's between this bad boy and this guy here. Okay? What is this space? This is a set of three-dimensional points. So this is a solid of three-dimensional points, so that X and Y are in R, but Z is in between the XY plane and the surface. That's the solid that we're trying to find the volume. Okay? So that's going to be your goal. Find the volume. Actually, let me write that over here. So your goal is to find the volume of the solid between F and R. Between the surface of F, and the region R. That's our goal. That's what we're trying to do. Okay? I'll close all these apps here. There we go. All right, and so just the way we did with Calc 1, we looked at a restricted domain AB and we split it up into slices. What we're going to want to do is we're going to want to get our region R, and we're going to want to slice it into smaller little rectangles. Smaller little rectangles. That's the strategy. Just the way we split up the line segment into smaller little line segments. And so the strategy is to partition R into small rectangles. We're going to call them Rij, all with equal area we're gonna call delta A. Just the way the intervals all had the same width, delta X, all these rectangles will have area delta A, which is found by partitioning the segment AB, just the way we did in Calc 1, into equal little line segments, all of width delta X. But now we're partitioning the Y line segment into equal line segments, all of with delta Y. And so what's the area of each little rectangle? Its width, which is delta X, times its length, delta Y. So all rectangles will have this as its area. All of those are Ij rectangles, okay? Where, what is Rj exactly? Sorry, what's R1? What's R11? It's gonna be, we're gonna use this notation. So this is gonna be R11 right here, this bad boy. What is it? It's the interval where X varies from X0 to X1 cross where Y varies from Y0 to Y1. So then what's R12? You're going to use the first digit to tell you the interval with that X is in. So it'll still be from X0 to X1 cross. But now the second digit tells me that this goes from Y1 to Y2. So you guys see these numbers right here? That's what makes these up. Okay? So then this would be like R12, R13, R14. What would this one be? R21. R21. Yeah, because you're in the second interval here. All right, I'm not going to write all that. So dot, 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 I, J, which is Xi minus 1, Xi, cross Yj minus 1, Yj. Yeah, Ben.
Wouldn't it be the opposite? So the one above R11 would be R12 because one is for X and then two is for Y, or?
Oh, yes, you're right. You're right. Yeah, this is the first interval for X, the second interval for Y. You're right, Ben. Sorry about that. Yeah, this is R2. Okay. Okay, so that's basically right now setting up how we split up our rectangle, just the way we learned how to split up the line segment in Calc 1. And so what are we going to do? If you look at the picture below, now that we've partitioned our rectangle just the way you would choose like a left endpoint or a right endpoint, but that we saw eventually, it doesn't matter the point, you just have to pick a point within the interval. We're going to just pick a point within one of the sub-rectangles. And that point will have some X value. If this is the Rij rectangle, the point will be Xij star, Yij star. Okay? You're going to get that point.
So at those points randomly picked.
So you can strategically pick them just the way you did a right endpoint in Calc 1. You could do like the top left endpoint. So you can, for all the rectangles, you can choose all the top left points, or all the bottom right, or all the midpoints. Similar stuff. Luckily, I'm not gonna have you guys do too much of that. Okay, I think there's probably like one problem. That's it. So then what do we do? Well, just the way in Calc 1, we approximated the area by adding the sum of all the areas of the rectangles. We're going to create all these rectangular prisms above above these subrectangles. So for example, I'm gonna get this Ri subrectangle, get a point, plug it into my function, so it gives me a z value on my surface, and then I'm gonna find the volume of this prism, this rectangular prism that I created here. Like that. Yes?
On the image above, there's all these little dots that are like kind of not all aligned. What are the dots?
So remember in Calc 1, here's A and B, how you pick a right endpoint or a left endpoint, but then I was saying that because the intervals get so small, you just pick a random x value. You just have to pick a point within the subrectangle, yeah, at random. If you want to have more of like a pattern, that's what Young Yang was asking, then you would pick all the top left ones instead.
The image is just showing you that theoretically, once you choose.
Exactly, yeah, because what's going to happen is we're gonna create an infinite number of subrectangles, and so eventually all those points are just gonna be relevant. Yeah. Okay, so here a little part of the warm-up. How would I find the volume of this guy?
Delta x times delta y times f of
The area of the base times the height, right? Which we know how to find the area of these. These all have area delta A. Okay? So, to approximate the volume, what we're going to do is we're going to approximate it with the volume. No, let me write this again. To approximate the volume above Rij, right? Because this is going to be a flat surface, but versus the surface of F is really not really, it's going to be a little slanted. Okay? We're going to take the volume of that prism. So the volume of prism above Rij. How do I find the volume of that prism? Well, it's going to be the height of the prism times the area of its base. The way you guys told me on the warm-up. Right? On the warm-up? How do we find the height of it, though? What is its height? Yeah, the z value you get from that, right? So that height is going to be your f of xij star, yij star. Okay? And then all of these have area delta A. They all have area delta A. But that delta A is found by your delta x and delta y. But let's just leave it delta A for now. Yeah, let's just leave it delta A for now. And so then, if I want to find the volume under the entire surface, so the volume of the total volume that we're looking for, we're going to approximate it by adding the area of all these sub-rectangles. But here's where it's going to get weird. Here's the area, the volume of the sub-rectangles. Here's what we're finding. This is what we're using to find the volume of all the sub-rectangles, okay? So this is how we're going to do it. We're first going to add, with respect to the I variable changing from 1 to n. Sorry, 1 to m. Sorry, I just made notes. 1 to m. Is that drawn here? No. And what that means is, how did I write it here? Yeah. We're going to add it up so that we're changing each x interval. We're going throughout all the x intervals. And then you're gonna change all in the y direction, the j's here. So there's two sums. Let me slow down there. Where, let me write this part here. Where n partitions the x-axis and m partitions the y-axis.
The sum of n j equal 1 is 1. I think it's
Is it flipped? Yes, I did flip them. Yeah, let's do that again. Okay, let me do that again. Yeah.
Yeah, but why is it the volume, the price?
Yeah, because this is affecting the y intervals.
Why intervals?
Yeah. So if I go back up, this is why I need all these pictures in front of you guys.
This side should be a rectangle.
Yeah, so if I go back up, this is saying that you're going to vary I from 1 to n. So that means that you're going to have x1, x2, all the way to xm. So you have m subintervals. And then your j is going to vary from 1 to n. So that means that it goes from y0, y1, all the way to yn. So you have n intervals here. Okay? And so what you're going to do is you would fix one of the j's. Let's say you fix it to the jth interval here. And then you're going to find the volume of all the prisms going in this direction as you vary I. So you find the volume across all these. And then you go to the next one. Next one. And that's why there's a sum of a sum. This sum goes across this direction, right, for a fixed j. So you find the volume of all those subrectangles. Then you go to the next one. So then you're going to add the sum of all that row, all the rectangles in that row, plus all the ones in that row, plus all the ones in that row. That's where you get two sums. Yeah, but
So for these, we always assume that f of x, ij, whatever, is f x, y, like f partial of x and y, or is
no
no?
partials yet. No partials yet. This is just plugging in a point into the function to give you z.
So like there's a m partition on the y-axis and m partitions on the x-axis.
Correct.
So for every partition of m, there's n partitions on the y-axis.
On-
So they integrate together. Like for every m partition on the x-axis, there are n partitions on the y-axis.
Correct.
Integrate together. So
Yeah.
yeah.
Yeah. So for example, when j is 1, right? When j is 1, you're at this interval. And so then you're going to vary I so that you do the sum of this rectangle plus the sum of this rectangle plus the sum of this rectangle. So it would look something like this. You're going to fix j to be 1. So it would look like this. 1, 1 plus 2, 1 plus 3, 1 plus dot, 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 all the way to m1. Okay, so that would be the first row. Plus, that's just this part though. Now you go to the second interval, where j is 2. 1, 2 plus r2, 2 plus r3, 2, dot, 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 plus rm2. Right? So this sum right here is this sum right there. Okay? Where it's writing all the rectangles in that row. But then, because there's this row of sums plus another row of sums, that's why you need another sum outside. Is this your guys' first time seeing a double sum? Okay, I think so, because I don't think in Calc 2 they do that.
So the sums can like change places.
It can change places. That will come up in a little bit. Yeah. That will come up. Keep that in mind. Yeah, I could do it the other way. I could instead add all the ones in this column plus all the ones in this column, right? Like we could have done it the other way. So it's possible for you to swap the sums in this case. Yeah.
It sounds like the nested for loop in the programming.
Yeah. Yeah. All right, guys. So that approximates the total volume. So what are we going to do? We're going to take a limit as m goes to infinity and as n goes to infinity, so that you have an infinite number of subrectangles. Okay? And that's how we're going to define our integral. We're going to say for a continuous function f the double integral integral of f over the rectangular region R, big title, sorry. The double integral of f over the rectangular region R is, and since we have since we have a double sum, we're going to use two integral symbols. Exactly. Okay? But this time we're going to say over R of my function xy. This time though, it's not delta x, it's going to be dA, because each subrectangle has area delta A, which we're going to approximate to dA, is that sum, but with a limit in front of it, where n goes to infinity and m goes to infinity. And it's basically copy paste of that over there. And delta A. So it's a limit, okay, which I'm not going to have you guys do, but it is a limit. Yes. Sure. No, yep, go for it.
Row, the first one's like row.
You mean these numbers here?
That's the first row plus the second row.
The first number will control which subinterval is in the columns. Yeah, so this one controls the columns, this one controls the rows. So this is saying all the rectangles in the first row. Yeah.
So in this instance, these are the first row plus the second row.
Exactly. Yep. Exactly.
So why is it the volume of Python?
What, volume of what?
Why is that a Python?
This guy right here. So what we're doing is, let me go back up here. So this volume here, under the surface, just above this R here though, this volume here over the surface is going to be approximated to be the volume of this prism, which is not the same thing as the one on the surface though, because the one on the surface actually has some kind of curvature like this, while the prism's just flat. So that volume of this small space above Rij is approximately the volume of that prism, of that little that long rectangular box. Okay?
Okay.
All right, if this limit does exist, then we say f is integrable over R. Integrable over R. It's a funny way of saying that. Okay, that's the definition for a double integral. It's a beast. You want.
So how many integrations do we have to do to calculate that? Do we have to do twice or just do once?
If there's a limit, an infinite number of times. If there's a limit, I don't know if you guys remember from Calc 1, but most likely you guys didn't do a definite integral with a limit. What you did is you approximated it with a finite number of rectangles. You never were told to do it with a limit. because it's actually really hard with the limit. Yeah, you have to use you might have to end up using like your converging series tests and all that stuff. Woo! Oh, we're not gonna do that. Yeah, all that good stuff. That's right. Comparison test, ratio test, and all that, just to see if it converges, right? It's harder to say what it equals. So we're not gonna do that. Okay. What we're gonna want to do is somehow use the fundamental theorem of calc, right? Where you guys can just plug in the endpoints and subtract them. We can use that. Whew, that's gold. But getting there is going to be a little bit of a journey. So one thing to note, if the z values of your function are always are non-negative, if they're non-negative over R, meaning that your surface is never going to go below the xy plane, then we're going to interpret this definite integral as the volume. How did I write it here? The volume between the surface of F and the region R. Okay? So yes, all you guys are asking all the right questions. Like, do you have to take that limit? I'm not gonna have you guys do limits. They're really, really, really challenging. So let's start by looking at an actual example to put some of this stuff together here. So let's consider this function here. 16 minus x squared minus y squared. Jacob, yeah.
Why does x have to be greater than 0 over R? Can we just say it's just the sine volume or something like that? Can we say sine area with
I could say sine volume, except that when it's like underneath, you like some of the volume, negative volume subtracts with the positive volume and all that. So that's why. Yeah. So, okay, so remember in chapter 12? Oh, sorry, Dylan.
The stacked limit there, n to infinity, those will exist under the same conditions as normal limits, right?
Yeah. Technically, there's two limits. There's like a limit and then a limit, but you just write it like that so that you don't have to write two limits. Yeah. But yes, you're totally right. All right, guys. So in this chapter, you're gonna have to use your chapter 12 knowledge of surfaces. Okay. So you got to remember, you're gonna have to train yourself on what cones look like when you see the equation. Paraboloids and ellipsoids, all that stuff comes back. Okay. All right. So we got this bad boy here, and we're gonna look at the surface of that function over R, which is given by the interval 0, 2 cross 0, 2. All right. Can I have you guys sketch this? Sketch what you think this would look like.
Just the region?
Sketch the surface, but then sketch what you think it would look like over this region R with your group. Okay? So try to sketch the surface of F to begin with, just to remember what that might look like. It might help if you replace this as a Z. Okay? Remember I gave you guys a sheet in chapter 12 with quadratic surfaces? You guys might have to bust that sucker out. Okay? And then try to remember what it would look like, but then try to sketch what it looks like only above this region R.
Did say we were gonna use these a lot.
Yup.
But you're kidding, because we barely use them.
Nope. Unfortunately, I was wrong. I mean, I was right, but not until now, right? Okay, there you go. Okay, I'm gonna try something. I'm gonna move this here and stay only within here. Okay, that way I can use this part of the board.
Yeah, so it's gonna be like.
Ah.
And then it'll start way up here. And then it'll slowly like. So it'll be slowing down. And then it'll be up like cut.
If you wanna use traces, you know. It might help if you let one of these equal 0. Right, so you can say, for example, on the xz plane, when y is 0, what does that look like? What does that curve look like on the xz plane? Z equals 60 minus x squared. A parabola facing down, shifted of 16 units. Okay?
So do you read that interval range as 0 to 2 by 0 to 2?
Cross. I mean, you can say bias. It's okay. It's okay. Because the shape ends up being a rectangle, and in a rectangle, you just say like 2 by 2 or 3 by 3, right? But normally you would say, this is the set cross this set. And then, yeah, so this, remember, this is the x values, and then these are the y values. Let's see. And you guys see good shapes? See good shapes? Okay. So what is the surface going to end up being? It's going to be a paraboloid, because the traces are just a bunch of parabolas. Or at least the traces for the 2 plates here that we mentioned. Actually, let me go like this. Z, Y, X. Okay, so yes, it should be a paraboloid shifted up to 16, facing down. Okay? So the paraboloid will go like this, facing down, but because you're going to be, hopefully my orange marker works. Let's see. Oh, bro. Hell, it doesn't work. Shit. Whatever, I'll just use this one. Here's your rectangular region where x goes from 1 to 2 and y goes from 1 to 2.
0 to 2.
Sorry, 0 to 2. 0 to 2. So if I get this paraboloid and I only get this piece of it, what you're going to end up getting, though, is a paraboloid that goes up right above 2, right here, right above this 2 right here, and then kind of shoots towards this corner, like somewhere like this. And you get that little piece of the paraboloid like that. Okay?
We have to figure out the points there on the edge. At the corner.
You don't have to. You won't have to, yeah. So this is a paraboloid, right? This is the paraboloid's piece above that rectangular region. Okay? Can I move this down? Let me see. It does look cleaner, yeah. Okay, you guys see that right there? All right, so that's a paraboloid right above that piece. Look at that, beautiful. Okay. Okay, and so if I wanted to use the definite integral, right, the definite integral would give me the volume of that solid between that, right? That's what this is supposed to represent. That volume. Cool? We're not going to do with the limit though. Sorry, today's a lot of lecture because it's the first section.
The limit is just for the concept, right? How many partitions there?
The limit is to define it. It's to define it. It's to define it, yeah. But then we want to use some tricks to actually compute it. Okay? All right. So here's the idea, guys. This is what we're going to do. Here's the plan. But I'm going to have you guys take a break and then we'll compute it. But let me just show you the plan. This, I do need to have it on shared screen. So here's the plan. What we're going to do instead of doing these limits is we're going to fix, let me see, make sure I have it. We're going to fix an x value. And let's say we fix the x value to be 1. Let me bring it to 1. We're going to fix that x value to 1 right here. And what we're going to do, kind of like what we did with partial derivatives, we're going to let x be constant and we're going to let y vary. If I let y vary, then I'm only going to be looking at that curve where y is changing and x stays fixed to be x equals 1. So then what we're going to do is we're going to say, okay, well, in my rectangular region where x is 1 and on my surface where x is 1, I want to look at the area between that curve of intersection and on the rectangle where x is 1 and look at that area. So what that means is we're going to integrate where we have x be a constant, okay? And we're going to be able to, like you guys did in 14.7, you're going to plug in points into the function where x is 1 and you let y vary. So we're going to plug in f of 1 comma y, okay? That will represent this curve of intersection because that's where the points are going to be all 1 for x. We're going to integrate that to give me this area. That area will be like one sheet of paper. Okay? But then what we're going to want to do is add the areas of all the sheets of paper to create the volume. And so then we're going to figure out how can I find the area of any slice of sheet of paper depending on x being a constant. That's the idea. Okay? And we're going to add up the sum of all those areas of sheets of paper to finally give me my volume. That's the strategy.
So it's like for also like every individual like slice, and then just like find the area of it and integrate all of them.
Correct. Yep. That's exactly right. So that's the strategy. But let's take a break because I talked a lot right now and I don't like doing that. So let's take a break, get some energy. I know the class is funky right now because of the visuals and all this stuff, but hopefully I'm figuring it out.
So it's taken all.
All right, guys, we're gonna keep going. Okay. All right. So a little bit more of me talking, and then I'm gonna have you guys do some good integration stuff. All right, we're almost there. Figuring out how we're gonna use fundamental theorem of calc to help us out. So to help us compute a double integral using the fundamental theorem of calc part 2. That's the one where you plug in the endpoints and subtract them. We use what's called iterated integrals. So instead of doing limits, we're going to do something called iterated integrals. We're going to see what they are. Okay. And here's a strategy that I was mentioning. So we're going to fix. If we fix for our example, if we fix x to equal 1, then we're going to have that z can now be found through the function by plugging in all the points of the form 1 comma y. Right? So all the points that lie on the rectangle where x is fixed to be 1 will have coordinates that look like this. We plug that into the function from our example, and that's going to give us 16 minus 1 squared minus y squared, which just turns into 15 minus y squared. Okay? So let me move it to where it was 1. So you guys see the ZY plane? Let me see if I can do it so it can move. Hold on, give me a second. Give me a second. Okay. Do you guys see this piece of this parabola facing down? This is the parabola shifted up 15 units going down on the ZY plane, because this is z equals 50 minus y squared. On the ZY plane, you guys see this parabola here that's shifted up 15 units? In Calc 1, you know how to find the area under the curve of that, right? You guys know how to do that. So notice that now you have z is a function of one variable. So you can use Calc 1 integration to help you find that area. Okay? Since z is a function of one variable, we can integrate it so that y will vary from 0 to 2, since we want y to stay between 0 and 2. Basically, this part here, from 0 to 2. So the curve of that, on this and that. And when we do that, we're going to do the integral where y varies from 0 to 2 of this function here, where now it's just a function of y, dy. So we're using Calc 1. And that means I'm integrating y is 0 from 0 to 2. This function here is 15 minus y squared dy. So you go ahead and you use your Calc 1 knowledge, and you say, okay, let me take the antiderivative of that. It's 15y. This is 1/3 minus y cubed, where y goes from 0 to 2. I did the math there for you. You plug in the points. You plug in 2, you plug in 0, and you're going to get 82 over 3. Okay? What does that number represent? What do you guys think? Area under the curve, where what though? Where x is equals 1. Okay? Notice that if I let x be a different value, see, that changes it. That changes the height of the function, right? Because on the surface, I'm somewhere else on the surface. You see that? So that only finds the area under the curve where x is equal to 1. So this is the area of our, we're going to call it slice, where x is equal to 1. So now what if I want to, in general, just say, okay, let me just consider some fixed constant x and do the same thing I just did there to see what my area should be. But remember, x is a constant. Okay? We're going to do the same thing, but now we're going to assume x is constant. And so in general, if x is a constant, if x is a constant, we have that when I take the area where y goes from 0 to 2 of f of x comma y dy, because I'm only looking at the change in y since x is just going to stay constant, I'm integrating from 0 to 2 the function 16 minus x squared minus y squared, but 0 to 2. Yeah, otherwise the answer is 0 and we're done. Oh, right. I'm all over it today. Okay? This is only with respect to y varying. X is constant. So here's where you have to do partial integration. Yes, you have to differentiate with respect to y only. X is constant. What's the antiderivative of 16 with respect to y? 16y. What's the antiderivative of this constant with respect to y? Minus x squared y. And y with respect to y? Okay, there it is. All right. And then we got to plug in the endpoints, but here you got to be specific. I'm plugging in the endpoints for the y coordinate.
That's still same.
God dang it. I keep putting that.
Really want this one to be 0.
I do. I don't know. My brain's tripping out right now. You plug in the 2, you plug in the 0, you subtract them. I did that math for you. It's going to be minus 2x squared plus 88 thirds.
So you didn't like to find the partial x, partial integration?
Well, here's what exactly. So let's talk about what this answer represents. Okay? This answer represented the area of our slice where x is equal to 1, right? What do you think this answer represents?
Arbitrary x for a single slice.
Exactly. The area of a slice for the given x that's being fixed. If x is 1, plug in 1 here. You get minus 2 plus 88 thirds. You get that answer, right? So it's kind of like producing a function that you plug in the x value and it gives you the area of the slice for that given x value. Exactly. Yeah. Okay? Yeah, you guys are seeing it. Good. So what this represents is the area of the slice for the fixed x value. That's what that represents. So that's the sheet of paper. It gives you the area of the sheet of paper. So then what do we want to do? We're going to integrate that. We're going to add the sum of all those slices. Okay? So you're going to add the area of all those slices. Should I do it here? Let me see. Yeah, I'll just write it here. So then, therefore, the total volume, to get the total volume, what we're going to do is the total volume, which we defined to be this double integral through this iterative process, I'm going to integrate y first. Did I write f here? I'm going to integrate. Did I write 2? Okay. I'm going to do it with respect to y first, right? That's going to give me that result. but then I'm gonna sum up all the slices with respect to x now and vary x. So that now x varies from 0 to 2. But then I'm gonna do it with respect to x changing. Okay? Yeah. So this is a function that gives me the area of each slice. So this is how you're going to do it normally on your homework. The order of these dy dx's matters. It's telling you first integrate the function with respect to y first, the way we did it here, right? So you do that work individually. You're going to have to do all this work individually within here. So you do all that work. You end up getting that answer. Thirds. And then you got to do another integral, but now with respect to x. And your final answer, let's see, if I do that with respect to x, help me out here. What is that? Minus 2/3 x cubed, 88/3 x, where x goes from 0 to 2. I believe I did the math for you there. Let me see. Yeah. And you get 160/3. That's the volume between the surface and R.
Can we integrate x first and then integrate y?
You read my mind. Okay.
Yeah.
So what I want you guys to do, okay, is what if instead of having x be constant, what if I had y be constant instead? And instead, I varied the y first. I fixed the y first. So what if I did the opposite order? Like that. Okay? Should we get a different answer?
No.
Oh, no. Should be the same answer, yeah, but I want you guys to do that. To practice. So what I would like you guys to do is do the same problem, but now do it with respect to x first and see what you get. Dx first, and then dy. Let's try it out. Yes. You can have very, very different, yeah. The next theory. So guys, I want you to practice it because I need your brain to start doing partial integration. Practice partial integration because the worksheet I'm going to give you gets spicier with nastier functions. Just practice it so that your brain starts doing partial integration. I know. That means you're going to have to do partial integration with like a U sub, partial integration, yeah, I know. Yeah, you're just pretending one of the variables is done. Everything you did in top 2. Yeah.
So the double integral is called the partial integration?
No, it's called the double integral, but when you're doing the work here, you're partially integrating. Or it's called an iterated integral.
Do we get like a special symbol for that? Like a partial derivative?
No, a special symbol is that you see that there's two things here versus just one. That's how you know you have to do that. Yeah. All right, as you finish that problem up, I'm gonna give you guys a worksheet to do with your group. There's a front side and there's a back side, okay? work on these with your group. Grab one pass it back, please. Grab one pass it back. Can you finish that guy up?
You give me half sheet? I have like.
Oh crap, I gave you the master copy. My bad.
Quick.
Hold on, where's the?
Oh, there's another one.
No. There should be only one that's,
Yeah, it's a top.
Did you guys get copies? Extras? Extras. You get one? Can you read the directions?
我啲片啲咧係都模仿啲，係啊，你有份。
Oh, you didn't get one.
我記得
So yeah, for the, you guys didn't get any. Oh, they went this way, that's good, my bad. But yeah, so practice problem, you should have got the same answer.
Actually, it's not too bad when you just track one dimension at a time.
Yeah. It takes a while to kind of get used to it, you get used to that.
Just imagine like an advertisement, count 3.
Twice the integrals, twice the integrals.
That's right, I know, right? Guys, for number 1, it just means do it where you do x first and then y first, and then try doing it where you do y and then x first. Okay? That's what number 1 is trying to tell you. You'll see that sometimes doing one way is easier than doing it the other way, depending on the function. Yeah. Sometimes you're like, oh, I can use some in this way, versus the other one I can't do use some. Yeah. So the puzzle gets a little bit more interesting.
Do you have to evaluate the inside one before you
do.
go to the
You do, yeah, you do.
I was like, hey, but then we got like capillary and I was like, no, that's not all. But okay, yes, that is super helpful. Yeah, I did that exercise.
First one is for the first grade, the second one is
Well, what would be the integral? What would be the integral of that?
Well, either way.
What would be the integral of this guy? It would be 5 cosine, right? So it's just the integral, basically this comes out, right? So when you have this, cosine y, you know how you could take out the 5? Guys, this might help you guys too, okay? You know how when you guys did this here, there's a rule where you could take out a constant? Okay? Well, if I'm integrating this, what's my constant right here? Cosine y. So just the way you could take out a constant, you could take out a constant. You could take out the cosine y so that the only stuff inside is the x part. That way you know you're just integrating that. Yeah, make it a little easier to see that. Well, that's what you gotta be careful. So see how here, you see how here when I integrated, I specified that I was integrating with respect to y. So I'm plugging in those values in for y. Here you're integrating with respect to x. These values don't go over for y, they go over for x. Oh, you need this part here? This phrase wrong. Let's go roll. We don't have questions, go walk around. Remember, for some of these, you might need some trig rules, U sub, partial fractions, maybe not, maybe partial fractions. Integral by parts, all that good stuff.
So how do I think I have to use this. So can I do integrate the same variable?
Well, okay, so let's say you're doing with respect to y, right? When you're doing it with respect to y, let's say right now x is a constant, right? So let's say you had something that looked like this. What rule can you use for that? You could use trig sub, U sub, right? Because here's y and then here's its derivative, right? Living inside there. So, or even if it was like this, you can still do U sub. So that's my hint. Okay, try to look at that problem like this.
In this class, are we gonna do any of these with the cinch and convex?
I don't think I've assigned any of those, no. You mean like with the integral, the antiderivatives of those things?
Yeah. Throughout the whole semester.
I'll try not to assign those, no. But It's hard to like predict that. Yeah.
Remember the top 2 professor saying, "You're never going to use these, but we're going to learn them anyways."
Yeah. All right, if you haven't, please check, just cross-reference with your classmates, especially the problems in the back. Those are tricky.
Yeah, that looks like trick zone. Yeah, that looks like trick zone. But the thing is that X squared. Oh, yes, you can.
My inside was
You can, and then. Oh, literally just no, I meant that. No, I was thinking so
I pulled the cosine out of there, and then I differentiate the sine. Like you can fractionally rewrite that, like you can negative cosine.
Because normally you
From 0 to pi of 2 was 1.
yeah.
Then it was cosine plus 1.
You took out the cosine y, right? But it's still multiplying.
Yeah.
Oh, that was multiplied in.
Cosine y.
Yeah, okay.
Never underestimate what we get.
Sorry, that's all I had.
Yeah, that's all I have to. I just started on the next one.
Much better because that just makes it like sine.
Oh, now it's straight simple.
Yeah, I got one.
You were saying your hands had like cosine.
You want to let u equals function. Let's say you let this u, right? Oh, no, I know. Which one is
Oh, that would be horrific. Really bad why. No, you just plug the natural log y back in. I'm requisitioning it. Why isn't your natural log squared? Now or over here. Buddy boy.
I remember nothing about how to do that.
Because the other integral is 1/3. Oh, the first part? So before I did the second integral, it's natural log 5 squared over 2x dx. So I might be wrong.
係咯。x 係 constant，你咧 x 係一個 constant，咁你個 x 一扣出嚟，咁就係成個答案成一部分。哦，係喎 x 係下。
Oh, the one is natural log 1 is 0.
Hello guys.
Natural log 5
真唔好，但我又考咗，我考咗6次考試，考到第一次全班第一次有 A，
They're not the same.
我最後一次考試，如果有一次考試考得3分就都係 A。我細個嘅中意 B。喺第一次考試之前就考完第一次之後就落 B。第一次係 A， 第二次同第三都係 B 啦，跟住第四、第五次全部 A， 即係一路 A 啦。如果唔係嘅話都係上課成
I was trying to remember if there was any.
You can't do that. That's cheating. You can't do that. No. Did he say you can do that? No. Not like that. No. That's different. Okay, this is completely different. This is two separate integrals. This is the integral of the same thing.
No, this is.
Still the same thing. Still the same thing. But you can't do these two separate. And okay, so I see that. But and you can't. You have to change your parameters if you do this. So when you use sub, you can't keep the same parameters. Because hold on. When you say u equal to ln and y, so 5u does not equal 5y. And then that might work. I would ask him. I don't think you can do that. I'm not confident. So you should ask him. Yeah. I mean, he's smarter than me. You have to figure it out. Here, do the U part. The rest the same. I want to see if that works. I don't know if it's right. I think it's.
Oh, damn it.
Can I do that? Because those go bye-bye, and I don't know if I can do that. I can do that. So, yeah, but then the x's go away forever. So won't that affect the equation at the end, or does it not change?
Well, remember that
Oh, I'm silly. I'm being an idiot. Ignore me. Oh, is this right? Before I start talking, because I think it is.
It looks pretty good, but the ln of 6 part is throwing me off. Let me see.
Well, because I got 2x on the bottom, so then that would be ln of 2x, so then ln of 6. Because this is before I do the second integral. So I have natural log of 5 squared, because I have u natural log squared, and then I have over 2x. And then for the second integral, I have 2 that over 2b. So I don't know. What do you have? That's not. Oh. So this.
You can find the derivative.
So you pull the 1/2.
Derivative, you want find.
Yeah. So you pull that out. And then. Wouldn't it stay in the natural log? Because it is a constant, but it affects the final answer. Because this doesn't go into the same. So does the 2 stay on the end, or does it go by?
Yeah.
So then we have to.
Yes.
At least you have the. Oh yeah, they actually might do that. That's weird. That's very simple.
Over 25.
Yeah, so it was over y squared, so that was 5.
I forgot where I was at that moment.
Oh, you're right. It wouldn't be. Oh yeah. So I do need to pull the 1/2 out.
I copied the problem down.
Oh, you just copied it.
Well, that would be a thing. So then that's just over 5 then.
Did you do that?
Try that. Why you write the solution of that? Okay. And then Ben, you can write, can I have you write number 2? Yeah, so.
It's this.
Oh, sorry, number 2.
Because I didn't run.
Yeah.
Because the integral of 1 over 2x is not.
And then Ben,
2x.
can I have you do number 2?
It's something else. You have to use of it.
Try to write big, okay? So people can read it.
Do I have to write like
Oh,
every?
not this one. Not this one.
Write all your work.
This is correct.
All your work.
But
Yeah. Whatever you wrote there.
yeah, that's the right answer.
So yeah?
Yeah, so it does work.
Oh, 2B, sorry, yeah. Can you change that to 2B? 2B, yeah.
Or
So
not
some- Ooh, let me see. Oh, no. So when you're doing tricks, you want to be strategic with the R days. You actually don't want to. Normally this is 4. But let's go. We want to have a value of 2. And then square it is 4. Well, whatever R you want to do, you want to start from the square.
X squared is y squared.
So then on the
There's no rule. In this case,
and then you know
When you bring it back.
Can I do this?
Split these, if they're divided by square. Oh, I meant that you go bye-bye, because it was so, I just did it all in one step. And so, this, so they, 2y, made that go away, so then it's just the 2 left over and the x.
oh, you already took the integral.
Oh, yeah, I already took the integral. Okay.
the derivative of 1 over y is ln.
The regular e because it's supposed to be x.
What did you say? U as 1 over y? Oh no, you're right. No,
Looks
derivative
close
of
to,
ln
looks
is
close to the answer, it's just like
yeah,
kind
yeah,
of
yeah.
format.
Yeah.
Thank you so much.
Thank you.
All right, guys, good job. Thank you, volunteers, or voluntold. All right, so let's take a look here. Both of these had some tricky U sub that was hiding there. So that's right. So here you have to integrate with respect to y first. So you would want to see, let me get my other marker so it doesn't, I don't want to waste work. So notice here that you have one, you can think of it like this, ln of y over x, where this is the derivative of this guy, right? And so that's why he ended up using u sub, letting u be ln of y. So its derivative with respect to y is 1 over y. And so then this became the u, and the 1 over y dy is what got replaced with the du. see that? Okay. And so, like I was mentioning earlier, this is just a constant. So you took the constant out, integrated u with respect to u. That would give you u squared over 2, right? U squared over 2, little integration property there. And then he undid the substitution by plugging in the ln of y back into the u, which gave him u squared over the 2 times the x and the y. Okay? And then remember, it'll be helpful at the beginning, at least for now, to remind yourself which variable you're plugging these things into. Okay? Because right now this is like a neat one. You might end up with a really nasty longer polynomial or something. Okay? So you plug that in here, you plug it in into y, and then remember that this is really just ln of 1 is just 0, so all that got canceled out. So you end up with just this fat constant now, and then you're going to integrate the x part with respect to x. So you took out that big old constant and just left the 1 over x part as a function. Right? There was this previous step here that looked like this. So he just took out everything that was a constant outside, integrated this. This is ln of the absolute value of x. Plug those values in. This is again 0, and so that's how you get that really weird answer. Okay. All right. Thank you. All right. Número 2. Let's see. This one, again, if this problem swapped these two, if I went like this, bloop, then you couldn't do u sub. Oh, yes, you can. I was wrong. You still can. I was wrong. It was this guy here. If this had dx first and then dy, then it's a completely different problem. It's a lot harder. Okay. But yeah, so in this case, you want to do u sub here. So notice that x here is the constant. X is here is just a constant. So if you let u be the y squared, you get y squared here. Take the derivative. You take the derivative here. Your du is 2y dy. So he just divided it by the 2y there. Plugged it in. So that the du here, the dy got replaced with du over 2y. That's kind of like a different way of doing it. And then notice that the y's ended up canceling here. And you replaced this with the u. Let's see where you took it from there. And then you got that 2 here. This is just a constant with respect to u, so you took out the x. This one you cannot take out, so you had to leave it. The step from here to here, there was another kind of technically a u sub that was done. Okay? Yes. You could have also done that. Totally right. You could have let that be that. So then this whole thing would have been u. So that this whole thing would have been u. And then when you undo the substitution, you still end up with the same result. Okay? Both of those would work. Yeah.
You have to write it as a partial of u, as opposed to du.
Partial of u. Say that one more time, William.
So if you have u equals x squared plus y squared, so then you would have like partial u equals.
No, because x is a constant. Okay. Yeah, x is a constant. Right now you're thinking of x as a constant. I think I know what you mean, though. I know what you mean.
I'm just thinking because
yeah,
when you do the partial, you think of it as a constant.
Correct.
We're already considering it a constant.
I see what you mean, though. Yeah, you're right. It is a little funky, though. I guess you could replace it with partial of u. It would still undo itself. It's just that I think what it is that when we do integration, we don't use partial. Yeah, which technically it is kind of partial because you're fixing one and you're fixing the other. You're right. I never realized that. That's a little not good notation. Yeah, actually, it would have been better if they did use partials here. All right, so let's see. So we do a little bit of u sub here, and then you plugged it in here for which variable? With y, right? Because that's the one you're doing. So you plug in into the y's, and then from each of these, now these are just a Calc 1 problem. You have to integrate both of those. And so you separate it into two integrals. Okay? That's a Calc 1 from that. All right. And so you should get an answer that looks something like this. I think the one I have in my solutions, God, what does it look like? 2 over 15, and then I have, I think, 2 root 2? Or root 2, huh? 2 root 2 minus 1, that's right. So some form of that answer is hopefully what you got, okay? These are going to be tricky, okay? So try not to start them the day before class, before they're due, right? Because they're going to take a while to do. Any questions on these? Anything you'd like to see again? Yeah, Dylan.
In the answer, over here, where did the 5 over 2 go?
So 5, this is, here, let's go like this.
I see.
It's okay, if you had that question, I'm sure other people have that question. So it goes like that. So remember that you can write this as square root of 2 to the 5th power, yeah. So you got, this is 2, and then this is 2. 2 times 2 times root 2. All right. Good stuff. Good job, guys. Sorry, see, doesn't it hurt to erase your work? It always hurts me when I have to erase my work. All right, so I just have one last thing, and I think we'll be out early today. Yeah. All right, the last thing I wanted to mention is Andres was asking me, what if I don't have the same like endpoints here? Like, what if this was 0, 5 and this was 2, 3? Can I have switched these as well? Okay, and it turns out you can. It has a special name. It's called Houdini's theorem. I believe he's an Italian mathematician. You might hear him a couple more times if you end up taking more math. So Houdini's theorem says that if f is continuous over R, where R is given by where your x is bounded by A and B, some rectangle here, and your y is bounded by C and D, then if you're trying to find the double integral over that region of your function, you can do it with respect to x first. And then do it with respect to y. Normally, you don't write the parentheses, okay? Your textbook will write the parentheses, but when you're doing it, it's very helpful visually if you want to use a parentheses. So this iterated integral is equal to the iterated integral we do it in this reverse order. C, D, and then x goes from A to B. And so instead, I do it with, I start with y first, and then let's do x. That's called Houdini's theorem. And so it works because the bounds of x and y are all numbers. That's why it works. Okay? When you guys come back on Tuesday, we're going to do general regions. And that it won't, these bounds will change. We're going to change a little bit. But you want to use this theorem because if you're given on the homework an integral and you notice that with respect to x is really hard, just swap it so that maybe try doing it with respect to y and you can use a different technique. Yeah. So yes, please take out all your integration notes from Calc 2. All right, this is the last thing we're going to talk about is the average value of a function. Then we're done. Just tell me I'm still recording, right? Yeah, okay. All right, guys, so hopefully, maybe they mentioned this to you in Calc, either Calc 1 or Calc 2. So let's say from Calc 1 or 2, not sure which part there. If you're given a function where y is a function of x over some closed interval a and b, so you got x over here, you got y over here, and then you have, use my green one. And then you have the graph of A, of F here, let's say this is A, and this is B. And the graph of F, let's say, goes like this. Let's say you consider all these possible y values, and you want to say, like, on average, if I picked a random x value here, what's the chance, like, what's the most likely y value that I'll get on average? Okay. And so the average output y value turns out to be what we're going to call the average of the function on that interval. It turns out to be the integral from a to b of your function. Does anyone remember what you had to multiply it with? I heard 1 over b minus a. Yeah. So basically, what this is kind of saying is you divide the integral by the length of the interval. Okay? By the length of the interval. And the value that you get, that number that you get, gives you the average y value out of all these possible y values on your function. Okay? And so if you guys see the very last picture on the 15.1 packet, it shows like a mountain with like water. You guys see that picture on your packet? I believe it has it. It's like a little mountain range. It looks something like this. Does it have that picture? Yeah, right, okay. So let's see what that picture is trying to say. So in Calc 3, we have a similar result. Given a function where z is a function of x and y over some rectangle a comma b cross c comma d. So you have some rectangular region, you have your function. The average output z value, which again we call f average, is going to be the double integral over that region R. And what do you guys think it'll be? This is 1 over the length of the interval that you're integrating over. So it's going to be 1 over the area of the region of your rectangle. Area of R. Okay? which your textbook I think calls, yeah, I'll just leave it like that. I think he just calls it A of R. Nothing fancy, but I just wanted to spell it out in case you're like, what the hell is that? So if I get that double integral and I divide it by the area of my rectangle, that gives me the average z value out of all the z values on my surface. So I wanted to kind of show you a picture of like an application of that. You can create, if you have some kind of function that can model some mountain range or some land space, and you wanted to know like the average height of that mountain range, that's kind of what this is representing. This is the average height of this mountain range. Okay? And that's it for this section. Hold on, question? No.
This applies only to definite integrals?
This applies only to definite integrals. We're not going to do indefinite integrals. We're not going to do indefinite integrals in this chapter. I think we might do it for chapter, they show up a little bit, I think in chapter 16, I have to remind myself, but not in chapter 15. Yeah.
Don't forget plus C.
Yeah.